man who virtually needs no introduction. He's has basically family in this group. And his lectures have been among the ones I recommend the most to engineers, researchers, students over the past few years. And it looks like he's got another real winner for us. Harvey Fiala has a master's in electrical engineering from Caltech. He's been an engineer for longer than most of us have been alive. And he's a representative of 3 generations of his family here in this room today. So let's please welcome Harvey Fiala.
Thank you, Mike. Yeah, there's 3 generations here. Actually, my wife, Bonnie, is right there. Bonnie, please stand up. And my son John here is in charge of almost everything. He's our firstborn, and his firstborn, John Arthur, is up manning the camera and so forth upstairs there. So, but we're going to have a little demonstration here, and it reminds me, someone else, a previous speaker, mentioned the Royal Society of London, and they've been in existence for 300 years or so. And about 30 years ago, Eric Leithweight, he invented the monorail type systems, and he's a true genius, mechanical engineer. And he had a demonstration of he had like a 4-foot rod on a 40-pound weight that was spinning a rotor, and it's hard to lift something like that up. But he showed that if you got it spinning, just make sure it doesn't dig into the floor, got some shield around it. If you got it spinning, you could lift it up and overhead. And I built one of those like 16 years ago, and John, in his very, very busy schedule, made another one rather hurriedly, and he's going to demonstrate it. I'm going to mention right now that mine was just a rod with bearings on it, and I used a tool to rev it up. And our daughter, just a teenager at the time, she was able to get it over her head, see, with one hand. And Eric Leithweight used one finger, really, to lift a 40-pound weight at the end of a rod. And it just, and I've even talked to, okay?
After we get done, anyone who wants to work with you, after we get done, anyone who wants to can come here and try to pick that up. That flywheel is 28 pounds. The whole assembly weighs about 43. You notice when I turned the wrong direction, I almost couldn't hold it and it almost grabbed the ground there. But as I forced precession in one direction, it not only raised up, but with one hand at one point in the middle there, it was climbing, and I had to grab the bottom with the other hand just to keep a grip on it there. This is very crude. The one that he designed and built years ago is much better. We're still working on getting a model that maybe someday that the audience could try to participate in, but if you want to come up here and lift us up afterward, come on up. Back to you, Harvey.
Okay, the Royal Society of London, someone mentioned they're kind of a snobby. Well, that's an understatement. And every month they have a speaker, like Marconi or all the famous scientists. They were allowed to come up and give a presentation, and it would always be published. Now, when Dr. Leithweight demonstrated this on stage, it's like as if they were accusing him of, saying that Newton's laws are wrong. And that's heresy, that's a sin. And they never published it, and they blackballed him from the Royal Society of London. And if that was their thinking, that could have been right at that time. It wasn't, but by now they should realize they made a serious mistake, and the Royal Society of London should issue a worldwide apology for having made a mistake like that 30 years ago. And okay, in my introductory remarks here, you'll notice a certain theme. It has to do with like the speed of gravitational interaction, which relates to the speed of light, and maybe the interaction is instantaneous, and that has a lot to do with mass and inertia. Now, I'll just mention that like 55 or 57 years ago, my first college physics course, after class was over, and there was like 100 students there on the rows, I walked up to the instructor and I asked him a question. I said, suppose you're out in deep space where there's nothing around for trillions of miles, and you put a ping pong ball out there, and it's just sitting there. Now you go 186,000 miles away. That's how far light travels in 1 second. And you go 186,000 miles, and when you say bingo, at t equals 0, you create a new planet. Now I asked him, how long will it take for the gravitational field from that newly created planet to reach out and grab a hold of that ping pong ball? You know what his answer was? He looked at me and he says, are you crazy? The times weren't right yet, but later on, that became the subject of devices for the generation and detection of gravitational radiation. That became my thesis at the California Institute of Technology, and I worked at Hughes at the same time, and I had a project there. They sponsored it to try to measure the speed of gravitational interaction, and Dr. Feynman was my instructor there in physics and mathematics, and I presented this to him, and he convinced me that the method I was using could never measure the propagation velocity of interaction of gravity, and he convinced me, so I actually terminated the project at Hughes, although he said that general theory of relativity assumes that the speed of propagation of gravitational interaction is at the speed of light. And so far that's been an assumption, but I think that it is actually wrong. And at that time, transistors were just coming into being, and a four-function calculator didn't exist. In fact, if I'd had a four-function calculator, they'd either burned me at the stake or made me God or someone. But since then, we have supercomputers now, and they've shown that with the sun and the planets around it, if the gravitational interaction wasn't instantaneous, these orbits would not be stable, and they can propagate that out for 1,000 years or 1,000,000 years or something like that, and show that if it's instantaneous, the orbits are stable. If it's not instantaneous, these orbits are going to degrade. So to me, either the speed of gravitational interaction has to be trillions of times faster than the speed of light, which for all practical purposes is instantaneous. And this leads up to the term quantum entanglement. All that means is that, and the term action, as the scientists were like afraid to say that gravity acts instantaneously. And now they attribute the property of inertia, which is my whole presentation. Any mass has inertia because it's connected to every other atom in the whole universe. That's what gives it inertia. If the mass of the universe changed, the inertia would change. And in our lifetime, we'll never observe a change in the mass or the inertia, rather. But quantum electrodynamics means that they've taken a light beam, split it into two, and when they operate on the one part, the other part knows instantaneously what happened here, and they're connected like. And so, and another interesting thing, Stephen Hawking he's in a wheelchair, but he's one of the most famous physicists alive today, maybe arguably so. He invented the Big Bang Theory, which says that sometime like 5 or 6 or 10 billion years ago, bang, there's a big explosion and all the mass went out to where it is now, although it's receding, they say. That all happened in a fraction of a second. Well, I asked him, he gives a lecture, he comes once a year for a whole month and stays at Caltech, and he lives in Cambridge, England, across the pond. But I asked him, if in the Big Bang Theory everything went out to its place within a fraction of a second, how can you reconcile that with nothing can travel faster than the speed of light? Okay, 2 years in a row I've asked him that question. I get no answer. Anyhow, that gives you some substance that the speed of gravity is probably instantaneous. And a little over a year ago, I was walking along the beach in California, and I saw a bottle float ashore, and I picked it up and it had a cork in it. I pulled the cork out, and lo and behold, a genie popped out. And this genie said, "Mister, I'm a genie. I can grant you a wish. Anything you want, I can grant it for you. So think it over carefully." And so I thought it over carefully, and I said, "Okay, I'd like you to deliver to me an inertial propulsion engine that weighs 1,000 pounds, and it can propel a 1,000-ton spaceship up to warp 10 in 10 seconds, and it must not be greater than 10 by 10 by 10 foot cube, and I want an instruction manual with it and all the blueprints for it." And the genie sort of just about laughed at me. He says, "Mister, you don't know what you're asking for." He says that what you've asked for, that your society hasn't discovered 3 new elements which would take to make that, and another dozen alloys which are strong and light that you haven't uncovered yet. And you just don't know what you're asking for. And I looked at him and I said, "No, I do know what I'm asking for, and that's exactly what I want. I'm not uncertain about anything." And then he went on again that your civilization isn't ready for something like that. I says, "But that's what I want." He says, "Please, think it over more carefully." So I thought it over and I says, okay, instead, can you tell me exactly how a woman thinks? And he said, how much warp speed did you want in that engine? So that's the truth. Now, if this system will work, okay. John has a picture here. In the last minute, he was going to build a little test device that demonstrates inertial propulsion, and it's a high-quality item, and it's got a heavy rotor, and in driving over to this place, it got bent and damaged. So pardon? Okay. Yeah, there's a rotor which weighs a lot. There's a little motor, and this is a track that it goes around. You'll see more of that in the essence of my talk today is I'm going to describe my patent. Most patents are 2 or 3 or 4 figures and maybe 2 or 3 pages of text and a few claims, and here's a copy of my patent. It has 39 claims and 50 drawing sheets and 118 pages. And I got the thing filed in January, and it's now July, or now it's August. And I just found out the day before I came here, sorry about that. I violated the rules there. And normally they start working on a patent right away. Well, I've got an insight there, and they haven't started working on my patent yet because it challenges some of the principles of physics. Like if I move forward like this, the only reason I can move is because I'm pushing back on the carpet here and so my action is to move this way. There's a reaction. It's actually the Earth rotating backward a trillionth of a degree, see? And nothing can violate that. For every action, there's an equal and opposite reaction. And integrally tied in with that is the conservation of the principle of angular momentum. So if we built a device here which has wheels, but there's no powertrain to the wheels, it's disconnected. The wheels only support it to keep it from dragging, and it can move back or forth. They say that violates. Actually, it doesn't. It uses a gravitational field as an external force, and the gravitational field is that of the Earth with your device, and if your device moves, the reaction is in the Earth via the gravitational field, and so it doesn't violate anything. It helps you to understand better the physical principles involved. But see, this says that it challenges some of the stuff, and so there's over 100 patents out on inertial propulsion. None of them are any good at all. I've looked at every one of them. And this one here, it makes some fantastic claims. So instead of going to work on it, and something doesn't have to work for them to issue a patent on it. They make money on the patent. And it satisfies the inventor, it puts it on the wall, and he can brag about it. And so I make some claims here, and I have some background that, gee, maybe this thing works. But before they issue a patent or turn it down or something, they're sending it out to a couple of physicists to check it over, and so they can get the reaction from the physicists. Hey, does this thing really work? Is it just another piece of junk? And they're not going to start evaluating it until they get this answer. And the physicist isn't going to flip to it and say, hey, it's a piece of junk, He's got to study it a little more carefully than that. It's got 51 figures in it, to which are substantial. And with that, I'm going to, with that introduction, I'm going to, okay, here's the cover page for the patent. Now, it's only a patent application so far. It's not a patent, but I'll give it a shot. I got to see if this little device works now. Okay, we'll stop here. About a month ago, I read something on the Tesla car coming out. They're going to make 10,000 of them this year in the USA, and they're supposed to get 210 miles on one battery charge, and they go 0 to 60 in 3 seconds or something like that. And I couldn't find that picture, but this is the one from last year. So, but see, I want you to all go buy Tesla cars. There's 10,000 of them out there, so it's kind of in line with the theme of our conventions here. So, and this is Stephen Hawking, the guy who invented the Big Bang and other stuff. And again, this is another kind of a cover page. Now, this is figure 1 in the patent. Okay, here's a half circle that's called a support ring, and here's a traction ring. And here's like 4 rollers, 4 wheels on which it can move. Now, there's no power to it. If it's going to move, it's due to inertial I guess I've bumped this a few times. And now that's a rotor. Now, dimensionally, this is not, you can't build one with these dimensions. This is to show the concept. And so there's a rotor, which is more of a ring, and there's a motor which propels it, which speeds it up. This is the battery, and this is the kind of a frame that holds it. Now, this traction ring, notice that little wheel there, it's splined to the shaft, so when the motor is turning it, it's turning like that, and it's carrying the wheel there, 104, as it comes from here to here. It carries the big rotor along here. Now when this traction ring comes to this point, it drops off and it doesn't provide any traction. At that point, the system is floating. At that point, precession starts. And so if you notice that rotor over there, it is actually on the inside of the traction ring, and so it's not supported. So it precesses from there over to here. And from here over to there, it's driven. You might say it's scooting or traction. So it's precession and traction, precession. And now, as it's the theory goes that as it's precessing here, a spinning, rotating mass that is precessing has less inertia than it does when it's not precessing. So let's just say we'll say it was a 40-pound object, and it had a certain amount of inertia about this axis. So when it's not precessing and it's being driven from here to here, it's like a 40-pound mass. But when it's precessing from here to here, it might be like a 20-pound mass, or a 15-pound mass, or a 30-pound mass. And the point is that if you can change its mass, which is the same as changing its inertia, you've got something to work with. Now, I've seen brilliant engineers that observed that heavy flywheel thing. They observe it happen, and their response was, "I only hope it's true." I mean, if I said, "Here's how it works," he could say, "I hope your analysis is correct." But if you see something happen, it's happening, man. It is true, and that's kind of a sad when someone says, "I only hope it's true." It demonstrates there's something to work with, and if you're creative enough, you can figure out how to use it. There's a lot of problems and applications on Earth. Figure out how to use it, and this is step one. That's one of the simplest possible implementations of it. Here's two. Now this is a little different. I'll back up a little bit. You can see that I didn't back up. Okay, that roller there and the traction ring, it's only friction driving it. It might slip or something. Well, if that was a V-belt, it'd have more traction. Well, this is 2A. Okay, here's where the support ring is on the inside of the rotor and the traction ring is on the outside. Let me go back and see what... here the rotor is on the outside of both rings. Here the traction ring is on the outside, but the other ring is on the inside, and it makes a difference. I won't bother to explain them all, but it's just a different configuration. It turns out that there's so many different configurations of this that it's kind of mind-boggling. Here's another one where there's a V-pulley, so you got good traction. And actually in this device that we'll show you later on, instead of a V-belt, he's got a gears there, which is great. And to get to that stage and have, you can compare some of this like to a Model T engine or a John Deere tractor is a two-cylinder engine, goes boom, 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 boom. And compare that now to a 12-cylinder Lamborghini or something like that. You know, there's a lot of development gone by. And once you get to the point of having gears here, you know, you're now paying $10, $20, or $100,000 for models that work. And now, okay, I'll back up a little bit. Notice that for half of this cycle, it's being driven, the other half it's precessing. And so during the precessing part, it actually moves backward slightly. And during the driven part, it moves forward positively. So there's a net movement. Now, that's a one-cylinder one, and that doesn't sound good to move forward and back up a little, move forward and back up a little. That just doesn't ring too nicely. So how about a two-cylinder job? Okay, I took one ring, I inverted it and put it over the other, and make a two-cylinder. So one of them is pushing forward at all times, and that's an improvement. Like I said, there are very many configurations to this. You can see here that the motor drives one of them, and these are gears. I just represent them as simply as I could. Here's another configuration where it's a two-cylinder one, so it's always moving forward, or it comes to a stop between movements, but it never backs up. And that's just a configuration. Whoops. And okay, I'm going to back up a little bit. Notice that these rotors are hollow cylinder rotors. They're thin-rimmed rotors. A rotor could be a solid disc, but these are thin rim rotors. If they weigh the same, you get better performance out of a thin rim rotor. And so now notice now these rotors are just small. Now it turns out if you take that rotor and reduce the diameter a little bit and widen it, and reduce the diameter still more and widen it, you keep that up, pretty soon you end up with something that's got a small diameter and long. And so that's what I call these rolling pin rotors. Now it turns out that the velocity that you can achieve is a function of the square of the ratio of the length to the diameter. And so you can see that if you can use a smaller diameter and a longer thing, longer axle or length, you will increase the velocity. You might lose horsepower, but one of the main things is to get the velocity. Once you have the velocity, then you just beef up everything in the right manner. And so this is what I call the rolling pin rotor. And this, if you go to nanotechnology, you'll find that you can make things like small as a human hair, and they're hollow. That would be like a cylindrical rotor, only now it's far stronger than steel and lighter weight than steel, and you can make it the length to the diameter ratio could easily be 100 or 100 times greater, and you can see that the potential there is great. And of course, I'm going to take up collections there so I can go buy a nano rotor system after this. Okay, here's a different configuration. And here's, here we got four rotors. Now notice if you have just two, one propels it and it comes to a stop, but the other one takes over. But the velocity comes to zero in a two-cylinder system. But in the four-cylinder system here, when it would come to zero, there's another one taken over. So it's always going. And I think that the ripple, I forget, it's less than 10% ripple. let me back up a little bit. Okay, this is one configuration. Okay, it's got one motor, and it's got a kind of a planetary gear system. It's important that the rotors all have the same speed, so this solves that problem. And now, I take the 4 rotors, I make 2 identical copies, and I tip one upside down, and I rotate it by 90 degrees so that I've doubled the horsepower, so to speak, and reduced the ripple, because now I think the ripple on the velocity here is like 3 or 6%. I've just forgotten. There's too many numbers. But again, whoops. Here, there is one motor driving 2 sets of planetary gear systems. I'll just leave it at that. And here, this is a solid disc rotor and a hollow disc, a thin rim rotor. And I have some equations which we'll get to. This is actually a very crude drawing. The others look much better. When I made this drawing, I had just bought a drawing package and hadn't, SolidWorks, 3D SolidWorks, hadn't really learned to use it. But this one works in a strange way. Actually, it precesses from here, and it bumps into that. Once it bumps into it, it stops precessing, and because it's spinning, it spins down here, and it uses traction along here. So it has its full weight here, and when its full weight is here, the reaction at the pivot point, which is transferred down to the base, the reaction, it moves forward the greatest. But then this is just a different view of it. Let me see. Anyhow, when it tractions its way over here, it goes up a little bit, and then it falls into thin air, and then it precesses over to here. And when it precesses this way, it backs up a teeny bit. And so it's kind of jerky, that's the first design that I made, and it worked, and it was kind of jerky. And but the later designs, which the very first ones I show, that the rotor always goes in a circle motion. It never has to reverse its direction. And for half the circle, it's propelled. For half the circle, it's precessing. And it's always at the same velocity. So it makes about 1,000 times more engineering sense. And this is a kind of a jerky thing, but it works. And it wants to jerk not just forward or backward, but it likes to jerk sideways a lot too. So now here's a very simple thing. This is just a concept. If you have a pivot point here and the rotor is spinning, it's going to precess over to here. Now, if you suddenly remove that pivot point and insert it over here, instead of going round and round like this, it's going to precess this way. And as soon as it touches a micro switch over here, you remove this pivot point, or you lower it, and pop up one here. And so it goes like this. And so if this, for example, were 12 inches here, and that was 12 inches, you've gone 1, 2, 3, 4, you've gone 8 feet in 2 full cycles. And normally the scientists, the physicists, have never addressed the issue. If you precess, well, on the average, the center of mass never moves. But if you precess halfway and stop, you got to tell them, look, the mass moved, didn't it? Well, they don't answer that question. They refuse to. They didn't know the answer. But the answer is that if it moved like that, the Earth did a counter movement in a very, very teeny-weeny circle here. And if you move it 8 feet, the Earth had a equal and opposite movement, which is in a trillionth of a trillionth of a trillionth of a degree and so forth. But that's perfectly explained, and this is just a simple thing to show that by precession you can move mass, and it's not free of charge. The reaction is in the earth. Whoops. Okay, this is for all the, I'll say the one-cylinder versions. When it's traction propelled, the velocity increases and comes down to zero, and precession starts, it actually backs up a little bit. And you say, wow, that's terrible. So if you have two of them, while one of it is backing up a little, the other one's advancing, and while this one which was backing up is advancing, the other one's going to back up a little. Well, you end up, if this was 5 units high, it's now 4 units high because this subtracts from it. So but there it touches zero, and that's not good either. You could filter that with springs and shock absorbers, but it's far better to have, let's see, combined velocity for 4 rotors. Okay, if you have, this is if you add the third and the fourth rotor, this is what you're adding to the previous one, and they're phase shifted, so that the result here, okay, you get 3.3 plus or minus 3.3% ripple, and and here, let's see, velocity waveforms for, this is just general. It applies toward figures 9, 10, 21, etc. Now, for that 60-degree thing, the very first one that I built, it didn't go round and round. It went 60 degrees, and it did something like this. Okay, the velocity there, when it would hit something, it would overshoot a little bit, and then this is when it's precessing, this is when it's tractioning, and so forth. But there's always a little bit of overshoot there. I'll back up a little. HMT stands for horizontal motion by mass transfer. The process of using a precessing thing to end up moving mass besides itself. It's the engine, but it has a payload. In a very, very simple case, you might say the payload weighs exactly as much as the rotor. That makes all the calculations very simple. But HMT stands for horizontal motion by mass transfer. Normally it'd be HMMT, but I just abbreviate it to HMT. And, okay, now we're done with horizontal motion. Thank you. This is a version that, okay, notice that the horizontal motion, it actually requires gravity. Gravity points straight down, and by definition, and precession is exactly perpendicular to the gravitational force, and it's in the horizontal plane. and so HMT requires gravity, depends on it. If you were out in outer space, it wouldn't work. Now here's something I call VMT, vertical motion by mass transfer. And in this case, here's a motor driving this, and it torques it round and round like that. And when you torque something, this is free to move up or down, and it's free to go round and round. Now in the operation of one of these, and I haven't built this myself, but this disc here, as it's being torqued, it's going to rise up an angle, and it could get up to, it'll be foolish to get this up at 90 degrees because the last 20 degrees doesn't give you much lift. The first, actually, a good way to operate this is from minus 30 degrees to plus 30 degrees. That's an equilateral triangle. And so if the length of the, what I call the lever arm or the spin axle, if that was 1 foot, then when it precesses from minus 30 to plus 30, it is raised 1 foot. And And that's the precession mode. So we'll just say that the mass of the rotors, the inertia was only half as much. So while they move up, it moves down. But then when you reset it with the reset rod, you stop the torquing, and so when you reset it, it has full weight. And so when it is pushed down with full weight, the base or the chassis or the vehicle moves up with more movement than it moves down during the reset stroke. And so now here's one. Now obviously this thing is going to the velocity will come to 0 and then go negative slightly during the precession stroke. And here again is a 4 version. Now that's a fairly tricky little yoke, I call it, that allow these, although these here move together, there's driven by one motor, this disc could move up or down plus or minus 60 degrees and not bump into. You can see that if this went straight across instead of arching up, and if this one went straight across, they'd bump into each other, and you'd only get a few degrees of motion. So that's a patentable one. That's one claim of my patent, the tricky little yoke there. But here there's 4 rotors, so again, it'll never come to a dead stop on the vertical axis. But now, in the Earth's gravitational field, you won't see this lift off. If you put it out in deep space and fired it up, okay, it's going to move. And it requires the ether. In other words, this light beam here, you can hear my voice because there's air here. If somehow we were in spacesuits and I spoke to you, you couldn't hear me because there's no air to conduct the sound. This light gets up to the ceiling because there's the ether, also called, used to call it pure vacuum, thinking that nothing was there. Actually, it's full of zero-point energy also. But if it were possible for this to exist and no ether, the light wouldn't travel at all. In fact, every single atom, its building block, it's built in the ether. You couldn't exist yourself if the ether didn't exist, and that's just the way God made it. The ether is the foundation of everything physical. Okay? Now here's the VMT, vertical motion by mass transfer, using RPR, rolling pin rotors. Can achieve a higher velocity. Now here, look at this. I went and I stacked 2 of them and staggered them at 90 degrees so that they won't bump into each other. And again, that gets the velocity ripple down to 3.3, plus or minus 3.3%. Now, I'll back up a little bit. Notice when that motor is torquing these round and round, if it's sitting down on something, now this base doesn't belong here because it's not for use on a tabletop or on the earth or on a track or on a road. It's just here for fun right now. But as that motor torques these round and round, the reaction is going to want to rotate. If this was the vehicle, as these go clockwise, these are going counterclockwise, the vehicle's going to want to rotate clockwise, opposite. Now that's obviously an undesirable effect. So, guess what? I have one there going this way, and this one here goes this way, and they're all in synchronism. They're all being driven by the same square wave, so that the torque generated by this system is canceled by the torque generated by this system. And hey, that's great. Now, okay, see, there's so many configurations that it's almost ridiculous. Here, I have 8 rotors on each one, two different stacks. Here, there's only 2 rotors on each one, but 4 different stacks. That accomplishes the same thing to cancel all the torques. And here, if each one had 4, let me back up 1 second. Yeah, there's 4 stacks. Whoops. And here, each stack has 4 rotors. Great. And here, look at that. Each one is a double stack. And now, this is a diagram which explains the basic precess reset cycle for a VMMT IPD. The word VMMT there could be a single M. This is the distance moved. And here, if it's down at, I'll say, minus 30 degrees, and its mass is M, and if the mass of all the rest of the vehicle, and including the central column and everything, was also M, that's what this assumes. Now, there's a forcing torque here, and as it is torqued counterclockwise, the spinning rotor starts to precess upward. And by golly, look, it precessed up to plus 30 degrees, which we have a limit switch there. At that point, the forcing torque stops, and a reset stroke pokes it right back down. But while it's precessing upward a little bit, the vehicle moves backward a little bit. Now, while it's being pushed down, it's moved forward with the bigger amount because there's full inertia there. And again, the cycle repeats. So, but the unpleasant thing about this, it moves forward, backs up a little, forward, backs up a little. But as we saw, you can overcome that by the... Now, this is just another basic, the forcing torque during precession, then it's turned off during reset. And the reset force is turned off during the precession time. And here, okay, the rotor angle, the rotor acceleration. If you have a spinning rotor like the one down there, and suddenly you remove the support under it, under the pivot point, it'll start precessing. And if in a perfect world it would get up to its acceleration, let's say it's spun once a second, which is a little bit fast for that. Let's say it's spun once a second. It gets from 0 angular velocity in the horizontal plane, it gets up to its angular precession velocity in 0 time, which is not physically possible. But this shows that it accelerates rapidly, and then the acceleration stops because it's constant velocity now. The velocity, theta double dot is acceleration. Theta single dot is velocity. So when it gets up to its velocity, the acceleration stops, and then it's going to be reversed, and so it stops its acceleration, it stops its angular velocity very quickly. Now, just to make it plain, I've shown this like 1 unit, and this is maybe 4 or 5 units, and here it crosses through the 0 point at 1 unit, and it turns acceleration negative. Then when it gets up to the other angular velocity, it stops accelerating. So that just, you need to, if you want to work in these or be an engineer or a technician or a service person, you need to understand the accelerations and the velocities. And here is the rotor velocity. Here it shows when it goes positive and negative, and of course this is for like a single cylinder system. This is the vertical velocity. We've seen that waveform several times. And precession rotor angular position. Okay, in the vertical one, it goes from minus 30 to plus 30, and we reset it to minus 30 and goes from minus 30 to plus 30. So that's, it's precessing up here and gets reset. And it's optimum if you make the reset time equal to the precession time, because then you can have multiple cylinders that are all properly synchronized. Here's just more waveforms. There's the forward velocity, combined velocity for multiple rotors, and again for even more rotors. Here's a picture of it's pretty tricky. You can imagine, just try to draw the darn thing if you think it's easy. This is one by itself, but to see it implemented with 4 of them, there's 4 rotors here, so that's a closer look at it. And here, now notice that the vertical one works in outer space. It'll also work in orbit, because in orbit, the Earth's attracting it toward it, but the centrifugal force exactly cancels the gravitational force. So it's as if there's no gravity, no centrifugal force, because they're canceled. In a circular orbit, they're always canceled. In an elliptical orbit, they're always canceled. But this shows that you can move side. Now, actually, in outer space, there is no up or down or sideways. But I always showed all those other figures. All those other figures were vertically oriented. Well, I'm showing here you can just tip it over and move horizontally too, although in outer space there's no such thing as a horizon unless you listen to Stargate, something like that. Okay, this shows that if you increase the forcing torque, the velocity increases as the forcing torque increases. Now you can keep that up only so far, because pretty soon you're going to, if you go past 60 degrees, fine. Once you get up to the top, you can't go past 90. So you got to design it to work within certain practical limits. But this shows you that during the torquing part, the velocity increases. And this is what I would call a preferred VMT embodiment. Here, if your forcing torque is a square wave input, you can actually shape the pulse to look something like this, and you'll end up with a constant velocity as it is right now. We saw that the velocity is like half of sine waves, and then you add them so that you get a little ripple. But here, you could shape the forcing torque pulse to end up with constant velocity, and you could shape the reset pulse so it's constant velocity also. Okay, now, someone here mentioned that in California at Lawrence Livermore Laboratory or someplace around there. Anyhow, for a mechanical system, for every mechanical system, there's an electronic analog. And here I work with motors, which are magnets and electric and magnetic fields, and gears and rotors a mass. Okay, what's the analog to a heavy mass in the electric field? It's the charge. How much does a charge weigh? Not very darn much. Electrons have a weight, but compared, and so there's the potential for something is so great, but I got to get a good mechanical model working so that I have a little radio control and I can make it move back up or turn corners, and there's no power to the wheels. It all does it by inertial propulsion, and that's using HMT, horizontal. Now, and then there's the vertical. And the VMT would best be tested in the space station, because there you're floating, see? And if they put the VMT version there and powered it up, it'd start either chugging along or go with 3% ripple on its velocity. When it gets up there, one of the astronauts had better turn it around or something, and they'd take good engineering data on it. But the only practical place to test that is in the space station. Of course, with some of these powered flights, you go up as high as you can and as fast as you can, and you shut the engine off and you coast in a parabolic arc at the edge of space. And some of those flights last for 45 seconds. Now, you could get a good test, but that's a hard way to do it. If you can send it up to something might weigh 5 or 10 pounds, send it up to the space station, and the engineers up there can test it for 6 months if they want to. But this here I just said electronic analog to motion by mass transfer, and I want some of you guys to fill that block in for me there, because I'm working on other things, see? So you guys, I want you to fill that in for me. Hey, it looks like we're back to the Tesla car. Now, okay, here's a figure. I didn't show all the internal hardware, but if you use 2, 4, 6, 8 rolling pin rotors for the rotors, this would increase the velocity. Actually, it increases the horsepower, not the velocity. There's certain limits on it, it's complicated. Now, there should be, okay, here's another figure. This is a different configuration. I almost have to look at my notes to see what's, okay, the base is a ring, and all the support ring and the traction ring are inside, and if you demonstrate this in a room, the bumper keeps, once you get a flywheel spinning, you don't want it to touch the floor. Eric Leithweight once had a small thing spinning at like 30,000 RPM, and suddenly it got loose, and it hit the floor, and it hit the ceiling and punched a hole in the ceiling. There's a lot of angular momentum that's built up, and if it hits something, it's going to turn it into kinetic energy, linear momentum, and you always want to make sure that, now the things I'm playing with are like less than a pound, but well, so is this little thing that Eric Leithweight had. But this shows a nice bumper. I forget if that's the main feature of it. Here's a stack of them. This is for vertical VMT. Now you might think, gee whiz, that's getting kind of high and it might tip over. Well, in outer space or in orbit, there is no such thing as tipping over. There's no up, no down. You can turn that sideways or leave it straight up. It doesn't matter, but it just shows that you can stack them. Next one, please. And I thought I had all these on a little thumb drive, but I must have. Okay, here's where you've staggered them and doubled the. They're all traveling at the same speed, though. Okay, next one. And here, more the same, I guess. Figure 45. Okay, this, there's no doubt, there's so many configurations. This shows the direction that it's supposed to travel. And here you can see that the gravity vector is vertical and the precession vector is exactly perpendicular to it, and that goes round and round. Next one. Now here's an interesting one. For HMT, horizontal one, something can, in a vertical gravitational field, something can only precess perfectly horizontal plane. And now, we're going to call this a bumper ring. And if this is mounted in an airplane or in a vehicle, and the vehicle goes up a steep hill, for example, this is a gimbal ring. Call that the pitch gimbal. That will allow the vehicle to go up or down at an angle, and it'll allow the inertial propulsion device to remain level. Now let's say you're turning a sharp corner and you're tilting. Okay, here's a roll axis, a roll bearing. So the vehicle can roll, or if it's an airplane, it can roll, and this thing will maintain its same attitude. In other words, it's a self-leveling type of device once you have the proper gimbals. In this case, a roll gimbal and a pitch gimbal. it'll remain working for you even though you're directing its energy at either up or down a little bit or to the side a little bit. Next one, please. Single rotor. This is an alternate configuration. Now this one here is a little bit tricky. It's actually, the direction of motion is in this direction. It doesn't show up here. On later drawings I have it showing up. But you have to consider, see, if this axle goes to the other side, it's like turning in the opposite direction. And so this vehicle is going to move that way instead of move this way, although it's a one-cylinder outfit. Next one, please. Okay, the previous one had the motor right here inside of this frame, but here the motor is near the center, and actually that's more ideal because the stator, a motor has a stator and a rotor, and the stator just represents dead mass. This is called active mass, and the rest of everything is passive mass. And the more passive mass you have, the greater the payload. And so you want to minimize the passive mass and maximize the active mass. How's the time so far, John? What's... okay, here's... and the rotor can take different shapes. I just created and each of the shapes has different moments of inertia and so forth. Now, I'm going to tell you a little story. We have a daughter who lives out in Las Vegas, and I was driving out to visit her once, and you know, Area 51, it's only about 70 miles north to west of Vegas. And I was going to drive out there and just look around, and I was tired once, and so I was still a few miles from Area 51. I wanted to rest, you know, take a short nap. So I looked at my watch, and it was 3 o'clock exactly. And I looked around a little bit, and I looked at my watch again. It was 14 minutes after 3. And I couldn't hardly figure it out. It was like if I just fell asleep for 14 minutes. Or is there some other explanation? I don't know. But, go to the next one, John. But I had something, there was an image in my mind. And this was the image here that just stuck in my mind as soon as I woke up, or whatever happened to me, see? So I'm not making any claims except that's how that image came to me. So, okay? That's just when you combine a traction ring and a support ring. Actually, you don't need a support ring at all, but that's in there so that if it fell out of precession, the rotor would dig into the tabletop or the carpet or something. And so, but this here combines 3 rings. I'll call it the bumper ring and a traction ring and a support ring. We just call that the control ring. Next, or maybe that's about it. There was one more which didn't quite make it. So let me look at my... I'll just talk... I tried to write this patent here as it's like a primer in inertial propulsion. It'll be it's probably for an advanced course, but it even has a glossary in it because there's a lot of terms. You know, for engineers to communicate, it's important to, like a lot of engineers or non-engineers say, well, you got to give it a little more juice. What the heck is juice? You know, amperes, torque, and so there's probably 100 different terms that I use, and I explain, exactly how I use them. And if it could have different meanings, I say what meaning I am assigning to it. And some of them are new terms that I have just created. And yes. Okay. Back up one more, John. Okay, here, notice that this has a unique property. The center of mass of the motor and rotor is at the pivot point, and so its moment of inertia, they cancel each other. That's great. You don't even have to use the mass of the motor in the calculations because it essentially cancels out. Now, if the motor is totally on one side of the pivot point, then your equations get more complex. But of course, if the motor mass is small compared to the rotor mass, you can almost neglect it anyway. And this shows that only a traction ring, no support ring. But by golly, if something happened and it fell down, it'd dig into your tabletop then. So, but this shows the bare essentials. Now, if you're just a poor inventor, and you see that's got to have a battery or something. So typically, my device just have a pivot point, and I rev it up with what kind of tool is it? Dremel tool. I rev it up, and then I run my tests, and it's not powered, so it's slowly winding down. That's not a real good way to get a lot of hard data off of it. But this shows the bare essentials for. Now you could have a rotor, which is part of a motor. The outside would be a rotor, and the inside would be the stator. And the axle, this here shows the spinning axle, and that's a beam which holds the stator of the motor to the frame holding the rotor. And this is a little inverting wheel so that when the big wheel goes around like that, it's in precession. And when it comes here, it has to be in traction. If it wasn't for this little inverting idler wheel, it would traction in the wrong direction. So, and okay, so this is actually like a primer. And also, the term HMT requires gravity to work. And VMT doesn't require any external force. It works in the ether. And of course, it has to have energy. Like in theory, in 10 years, we might have 0-point energy developed so that there'd be an inexhaustible source of energy so you could go any place. And I've assigned a term. Okay, notice that my HMT just accelerates up to a certain velocity and can't go any faster. Now, and my VMT also reaches a vertical velocity limit. It can't go any faster. Now, something with sustained acceleration, I call that SA. Sustained acceleration is what you need for space travel. And I have a configuration which I've not been able to, haven't had time to build yet, but it uses gravity, but it'll produce, if it works out right, it will produce horizontal sustained acceleration, which will keep accelerating, and if you know, until the wind resistance stops it or something. Now, I've called that GSA for gravity-dependent sustained acceleration. Now, the ultimate is, I call ASA, ether. Ether spelled A-E-T-H-E-R, according to the way I use it. And ASA is ether sustained acceleration. That's the ultimate. And it would need 0-point energy or something like that to keep it going for months or years and to travel to the stars. So I think, one more thing. Our church has a Sunday bulletin. I'm not out here to convert anyone, but they have something each week called Holy Humor. And here's one. I'm going to read it to you. Words have power. Consider the effect of saying these words out loud to another person. I love you. Let's help him. Drop dead. I want a divorce. A single phrase can crush or redeem. It can also destroy a nation or save it. Let the bombing commence now. The aid package has been approved. We've discovered a vaccine. Now, if human language has such authority to make a difference, imagine the power in the divine words spoken. So far I've been talking about human words. In the divine words spoken, unlike human speech, which can prove to be false, God's word is always true. When God talks, all the molecules of the universe listen, organize, and respond instantly. Like if God said, hey, I want the world to end right now, you think it'd end and disappear? And a billion years later, his word would be traveling out and making galaxies disappear until it's all gone? No, if he says, hey man, that's it, it's all gone. It has to do with this quantum electrodynamics, action at a distance, and the inertia of a body. All the atoms in the universe are like in communication with each other. And the effect of a single atom on something else is not measurable. But once you get something the size of a star or a planet or a moon, then they have a significant effect on anything in their sphere of influence. So I just thought that the Word of God is instantaneous, and He created everything. He created the ether, and in the ether He created us and elements, and we've discovered only some of the elements, not all of them. We've discovered only a small fraction of the alloys that we need for the inertial propulsion engine that I talked about. Okay. Oh, okay. This is, this here is like a plastic thing from yogurt, maybe, I forgot. And it turns out that if you use wheels, they have a lot of friction for small devices. This is from a toy gyro. And actually I had that, I would rev that up with a Dremel tool to like 5,000 RPM, and son of a gun, the thing got bent right there. Bent by only about 2 degrees, and it vibrates, and so it's wrong. Now in other words, I was going to demonstrate a powered vehicle here, but less than a week ago it bent, and it's sort of self-explanatory. It pivots around that point, and it can move up or down a few degrees in elevation, and it's on a glass plate. And on the tabletop, it's measured inches, 1, 2, 3, 4. Now, as it runs, you can see it move forward a little, back a little, forward a little, back a little, forward a little, back a little. And I have under here some rollers, maybe they're 1/4 inch or less in diameter. And that's a very, very low friction way. And at first I tried it with 3 ball bearings, 1, 2, and 3. But then it lets it go in any direction. And so you see, right now the motion is constrained to backward or forward, and that simplifies life immensely. And there's one thing, see, it's easy to move backward or forward, but it's hard for that glass to slide back or forward. That's an example of static friction having to move sideways, laterally, and that's an example of rolling friction here. And kinetic friction is the friction of like spinning in the rotor. There's kinetic friction there, and there's some aerodynamic resistance of the atmosphere if you're going slow or very small. But if you now I took the next size larger tube, I cut about a 1/2 inch length and a 1/2 inch length over there, and I slipped it over it. And so there's a lot less, there's only 1/10 the rolling friction even. And if you literally blow at that thing, it'll roll, which is a very good, in fact, my wife thought about that configuration, so I implemented it, and this one does not show the larger diameters on the ends, but it works really great. And this is something that I was going to demonstrate this year, but it busted. Next one, if there's another one. Okay, here's just another picture of it. Now this here is a very, very good way to measure the inertia of a precessing spinning rotor. If you rev it up with actually it'd be nice to have a motor on it, but I rev it up with the Dremel tool and I raise it up at about maybe 45 degrees, and it goes round and round like this. And as it goes round and round, it moves back and forth like this. And when it lowers enough so that it starts tractioning, it tractions all the way. This one wasn't intended to have a net motion. When it tractions all the way, first off, when it's precessing, it moves back and forth by like maybe 1/3 of an inch. When it's tractioning, it moves back and forth a lot. And that's a direct ratio. You're not changing anything. Here, the motor's inert, but you're not changing one molecule of it. It's just that when it's still precessing round and round, its back and forth motion is a measure of the inertia of that rotor when it's precessing. When it touches down, it stops precessing, and if you calculated it so that it's still going at the same speed, then the forward and backward motion, I've measured just roughly, the traction motion is maybe 3 times that of the precession motion for my particular configuration. And of course, this is like a thin disc rotor. Actually, it's more like a torus or toroid. So it's an efficient form of a rotor for a toy. It is efficient. And here's another view, or the same view, I don't remember. I just took a batch of shots. Here's another view of it. What I did, I actually took some collars and I used super glue and I glued them to the sides. And then I used a screw, a smaller screw. This becomes the pivot point on the vertical axis. And this becomes the pivot point around the horizontal axis. And here, now this is a real tricky thing. If you notice that the traction ring stops right there and it drops down, and then that wheel is supposed to precess along here until it gets here, and it meets the top and it tractions all the way over here, and then it drops down. There's I'll say a 1/4 inch drop or something, and then it precesses here. And so when it's when it's tractioning from here to here, it moves forward, I'll say like 1.5 inches, and then when it precesses, it moves back a 1/2 inch maybe, then forward. So it goes like this, and this one actually works, except I'm a little ashamed to show working with stuff like this. I want one of you guys to give me $20,000 to make a good prototype, and after that, it'll take $1 million to develop production models. I'm just giving you a heads up on it. So see me right after this. This is just a closer view of it. You can see this is my little inverting roller there. Here's a example of one of our test devices. John built this, but we did measurements relating to the VMT on this, and it performs according to calculations. There's actually, these are 2 motors, and they both come off the same variac, and down here is the torquing one. So there's a second variac, and there's a motor right there that does the torquing. It torques it slowly while these spin at maybe 3,000 or 4,000 RPM. That's just another device. And here, okay, that shows one, I call them a variac. And I was measuring, this is a little motor. I was varying the voltage to it and measuring the rotor speed versus voltage. And here's the little voltmeter. Here's another device that actually one interesting thing about this, as it's precessing, all the weight is on the pivot point, and so it's not going to tip over. In fact, Eric Leithweight did a lot of this kind of stuff, and it looked like sheer magic. You know, it should have fallen off the table, but it didn't. And here's maybe this was when we were hooked up to it. Two different motors, one driving the torquing motor, and the other one driving the two spinning rotors. And here, maybe this is the last one for all I know. Finally, inertial propulsion is here. Okay? Any left, or is that it, John?
Okay, we've got about 3.5 minutes. We could probably have time to take one or two questions. If they're quick, we might have 3 questions. Anybody? Okay, we'll start right here. This is number 1. Number 2 in the left.
2 questions. RPM, never mentioned, and practical application.
Oh, okay, practical application. That's an extremely good question. You know, for example, I talk about a little vehicle with no power to the wheels, but, you know, some people are rich enough to go pay $500,000 for a Lamborghini, or even $3 million or something like that. And if you had, and it's got all the goodies on it, if you had a button called IPD for inertial propulsion device, or engage inertial propulsion, EIP, okay. Now let's say you're going up the mountains and you park on the side of the road and it's icy and slippery and you can't move. And all you got to do is push the IPD button, and it's like a giant hand comes from heaven and moves you right along. Of course, the size of that device has to be scaled to the weight of the car, but you don't need to get out of there at 60 miles an hour. If it moves you, it's like a strong man pushing slowly on the vehicle. You let it move you, who knows, maybe 1 mile an hour, or 5 miles an hour, until you get onto solid ground. So that's an example of using HMT on Earth, because there's I did have another whole batch of slides, like I show a dozen different examples for the use of HMT. Now obviously one big one is for a museum, have a big unit operating there. Another is you can build, once we get the design perfected and get the ratios and the speeds and all this, you can build an all plastic toy except for the rotor, which might be lead, and maybe a little motor on it. But you can see it is so simple, but the engineering is complex. Once we master that, I plan to go to Mattel Toy, and I would have done that except I want to get a demonstrable model that I can call in the television studios and have PhDs and NASA come and witness it. Then I'm going to turn loose with about a dozen different things. Mattel Toy is one of them. And then I'm not trying to be secret about it. When a toy is built, the theory will be released to the whole world. Then, for $25 you can get a cheap toy. For $50 you can get a darn good one. And that's an example. Also, an example of vertical VMT. In February, there was a military had a spacecraft up there, a military intelligence one. Somehow it didn't reach the full orbit or something, so it was useless. They could have used up all the fuel for the reaction jets that position it, keep the attitude, and station keeping. They could have used up all that fuel, and then it would have been worthless. And so they decided to deorbit it, shoot it down, and and so they used the fuel that they had to slow it down, and then they had 3 ships, each with some missiles. Fortunately, the first one hit it, which was great. That was a political job, but it hit the fuel tank on that spacecraft and blew it to smithereens. But instead of having a rocket to deorbit it, see, if you want to go to work, you got to get up to speed. You got to get up to 60 miles an hour like that, and then you stop. But if you want to deorbit something, you don't have to do that in 10 minutes. You could take 10 months if you wanted to. And so you could have I'll say a small VMT unit instead of one that's going to really move the thing along. And so you can use it for station keeping. Actually, the attitude gets off a little bit. You have to correct it. And the orbit lowers a little bit. You got to pump it back up. All those things could be done with the VMT unit. And NASA, I'm going to hit them real hard with that, with those. I've got a dozen applications listed. There's another case, the Russians, and they just blew it up because they didn't have the means to deorbit it. And I'm saying that the companies that launch satellites, like Hughes has that ocean launcher, and there's one at Cape Kennedy, and Russia has a couple of them, and China now has some, and India has one. Every entity that launches should provide, if the satellite user can afford it or wants it, we'll put one of these little VMT units on an inertial propulsion device on it. It'll cost you $50,000 or something like that, and they'll literally bolt it to there'll be the standard interface on every satellite. It'll have room for 4 bolts, and that's where you bolt the IPD. And then if they ever had to deorbit it, or station keep it, you don't need fuel any longer. Solar cells keep the batteries charged, and occasionally you use the inertial propulsion device for station keeping and attitude control, and ultimately, when the satellite's burned out or something, deorbit it, free of charge. And yet, this does not have sustained acceleration. Sustained acceleration is the holy grail of space travel to the stars. And what I'm talking about is the humblest of things, but yet it would save billions of dollars every year for all the space programs. Honestly, it would. And this one tractor, if a higher end car had an inertial propulsion engine, you could go all the way up to Lake Big Bear on inertial propulsion only. You could. So, any other questions?
Actually, one quick comment. Since March 1987, 91% of all space shuttle activities and missions have been refueling or fuel tasking for the purpose of station keeping or orbital maintenance on satellites. So that one right there alone. Or there's the ICS control, the inertial traction control, or ITC. You just, you turn your corner tight and you don't want to slide off. You just push the ITC button, and inertial traction control handles it for you. You don't even need those nice bank curves at Indy. Now here's the last question right here.
I'll make one comment before that. There's so many good applications. Of course, there's a million things that it can't do, but look at what it can do, and it makes me sick that the world... Now, this device isn't a threat to the oil companies, see? If you guys develop zero-point energy, you better look behind your back and make sure the oil companies aren't going to knock you out, see? This isn't a threat to any oil company thing, and so it just makes me sick that once I get a good development model, I'm going to try to get a $10 million grant or something like that to really hire a PhD and some engineers and a couple of machinists and so forth and build something. And I pray that I'll live long enough to do that. Yes, your question.
Let's go back to that model that you had, the last one that you showed us, the toy model. And that's where it's confined to operate in just one direction, either plus or minus along a straight line.
Yes.
Now, as I understand, what you're telling us is that this during the traction phase, the motor is connected to the track, and that torque then provides the movement in one direction, let's say X, along that line. And then when it comes to 180 degrees, all of a sudden the tractor track is removed out from under the tractor drive, and the precessing gyro remains suspended in space while it precesses the remaining 180 degrees. And that precessing force is much less, but in the opposite direction of the tractor drive torque thrust.
That's correct.
And that continues on and on and on, and so you have, and you say it's like 3 to 1, so it moves forward 3 steps, and then decelerates and move forward backwards about 1 step, and then move forward another 3 steps, and maybe decelerate, and then you add more and more of these, and you negate, and since the overwhelming torque force is greater than the precessive reverse force, you, with enough of them, all of a sudden start to get a rather smoother movement in the one direction.
That's correct.
And all the other inertial drives that you put on there were to confine the movement, given that it's not in a gravitational field or confined physically to one linear movement, to keep it on track in a sense.
What you said is correct, and you didn't actually have a question for me. You can now teach the thing.
Actually, in closing, may I finish responding to that, Harvey? And I have to apologize. Harvey did have a working model, but somewhere between Kimball County and El Paso, there was a little bit of a problem, and the unit was damaged and almost destroyed. This right here is in the process of rebuild, and if you look closely here, at the top end of there, at the rotor, there's a gear just on the outside of that engages the counter-rotating shaft, and there's also it's actually a rack and pinion gear type setup that it was installed around the circumference in this track right around here, so that it would precess through 210 degrees, and the remaining of it would, when the rack gear engaged, it ripped it so fast that actually on this one, there was no negative motion the first 3 times that we tried it. It was just battery powered, but we had something fall on it, and we had a shaft sticking out the top, and it bent the shaft and ripped the rack gear right out of the side there, and we just, in the long hours since we've been here in Albuquerque, we've been trying to rebuild it, but didn't make it in time. That's one of the difficulties with only getting an hour and a half of sleep a night when these conferences come along.
Only one other quick comment. By physics as we understand it now, inertial drive is impossible. Is that their stance?
Well, yes. What I've done is demonstrate that inertial drives are possible.
They are possible.
Now, there's one catch. The term inertial propulsion is almost a misnomer. Normally, see, like if you watch Star Trek or something, and you accelerate to light speed, you don't feel the effects. That's I'll call it a science fiction type definition of inertial propulsion. But in all these types, if you're sitting in the vehicle and you could get it up to 2 G's or something, you're going to feel it just like the astronauts. But in only God knows how to accelerate, say, to the 2 times the speed of light and not feel. In fact, the crazy scientists, they say that as you approach the speed of light, your forward dimension shrivels up and you become infinitely massive. And to me, I mean, last year I showed the equations that's all horsepucky. It really is. It makes a lot more sense. What I proposed makes sense. What they said, you can't even imagine it. So, yes, inertial propulsion is possible, but you're going to feel the inertial. You're going to feel the acceleration.
Ladies and gentlemen, Harvey Fiala. Okay, we'd like to take a very short break, and Ty Robinson's going to be back with us. If we can make the break between 7 and 10 minutes, take your comfort, hurry back, and then we'll have the social afterward. If you want to speak to